Hi everybody, welcome back to Info 3370, studying social inequality with data science. Today we're talking about a big idea of a train-test split. This is an idea that helps us evaluate out-of-sample prediction in the data we have available in order to select one among many candidate statistical and machine learning estimators. As a quick recap of where we are in the course, recall that we're in this section where we're talking about social mobility, whether we can predict a kid's outcome later in life as a function of characteristics of the family into which that child was born. We framed this as a prediction task and talked about how you could build a submission in our little challenge using ordinary least squares. Today we're going to talk about sample splitting as a way to choose one among several possible models you might use in your submission. So in supervised machine learning, the goal is to learn patterns in the available data and then predict outcomes for previously unseen cases. And we can think of this with this matrix representation where we have a set of predictors here, and we're going to learn to discover patterns in a learning set where we get to see both the predictors and the outcomes. The task is to predict for the new cases for which we have access to the predictors but we don't have access to the outcomes. So we'd like to predict those outcomes. In this case, that's to see how close we can get to the outcomes we really know in practice. And in real applications, this might happen in the world in places where you will never have access to the holdout set, and you really just want to predict because the whole goal of your prediction task is to predict for the cases where you don't know the outcome. So there's a big question of how do we know which method will perform well at this task? You might pause for a moment and think about that. Like, how would I choose when I have only access to the learning set which model to use for my prediction exercise? A key principle of machine learning is that when a task involves unseen data, we ought to try to mimic that task with the data we already have, then pick the method that performs best on our mimic task. So in this case, here's our task where we want to make predictions for these cases that we don't get to see. If we want to mimic that task, we might take our learning set and split it into one component that we'll call the train set and another component that we'll call the test set. Now remember, the entire learning set is available to you as the analyst, so you're going to actually use both of these sets in your analysis. You'll use the train set to discover patterns in the data, and then the test set to select which model among many candidates you're going to use when you then ultimately go to make predictions in the holdout set. So here are the steps to do a sample split in R. You'll first load the data, then create a train test split, learn candidate prediction functions in the train set, evaluate the predictive performance of those functions in your test set, and then finally, once you've chosen a model, you go back and learn that model in the whole learning set, and then predict for the holdout set where you don't get to see the outcome values. So to start, you'll prepare your environment. You'll want the tidyverse package and the R sample package. There are many ways to make a train test split. I'll illustrate it with the R sample package because it makes this particularly easy. A third thing you'll want to do is set your seed with a number of your choosing so that you can make sure that you have reproducibility despite random sampling. So we're going to ultimately randomly assign cases to be part of the train or the test set, but you want to get the same answer every time you run your code. So by setting the seed at the top of your code with some number you choose, then you know that every time you run that code, the random numbers will be the same, and thus you'll end up with the same result each time. First step, load the data. This is exactly as we've done in previous classes. Second step, create a train test split. So you can begin with the R sample package by using the initial split function. So here I'm taking the learning set, which is a data frame, and I'm piping that down into the initial split function. I'm telling the function that I want to use a proportion of 0.5. So half the data will go to training, half the data will go to testing. Then the training and testing functions will create data frames from this learning split object we've just created. So train is going to be a data frame containing the training observations. Test will be a data frame containing the test observations. Next, we learn candidate prediction functions on the train set. So I'll illustrate this with ordinary least squares. We might consider three models. Predict the respondent's income as an adult as a function of their parents' income. 2, as a function of their parents' income plus race plus sex. 3, that same model where we interact parents' income with race and with sex. If it's been a while since you've been in a statistics class, hold on for one slide and you'll get to see what this means when I say that we interact those predictors together. So to put these in R, we could just fit these three models. So here we're fitting candidates 1, 2, and 3, where we hand R the model formula, and then we hand it a data set. In this case, we're going to fit them on the training set in every case. Okay, so I just said I was going to explain these interactions a little bit. So in the first model, the only predictor is parent log income. So in that candidate model, we'll make the same predictions for people regardless of the racial category and sex category with which they've identified in the data. In the second model, we've included income and race and sex additively. This means that we have the same slope in every line because everyone's response to parent log income is going to be assumed to be the same by the model. Yet these lines are all offset by an intercept shift. So we assume that your predicted value is going to be some coefficient times your parent's log income plus some coefficient times your racial category plus some coefficient times your sex category. In the third candidate model, we interact these predictors together. Effectively, this says that we're going to take subpopulations defined by race and sex and then estimate the relationship between parent log income and respondent log income in each of those subpopulations. So before we get any farther, it's worth thinking to ourselves about which of these models we might prefer on conceptual grounds. Conceptually, I am drawn to model 3. If there were no data limitations, that's the model that I would want to estimate. Because in fact, I think the world is complicated, and I think subpopulations defined by demographic characteristics by race and sex experience different forms of, say, discrimination in the world, such that parent income might relate to the respondent's income differently in each of these subpopulations. But when we're estimating in a sample of limited size, there's a danger that what we pick up when we throw lots of terms into the model is lots of noise. So for example, I find it hard to believe that there's any subgroup for whom parent log income negatively predicts respondent's log income. I find myself wondering whether these slopes over here correspond to real patterns in the population or idiosyncrasies of the training set in which we happen to estimate the model. And this is the key benefit of a train-test split, that it's going to help us decipher between these real patterns and the ones that are unique to the training set. The next step is to evaluate predictive performance on the test set. So here we're beginning with that test data frame, and then we're going to mutate to create 3 new variables: the predicted value of the model from candidate 1, candidate 2, and candidate 3. In each case, we're going to predict in the new data frame test. So we learned in the training set, making predictions in the test set. Then to make the code simpler, I'm pivoting longer here so that we now end up with a data frame where we have a column called model, which says whether this prediction comes from candidate 1, 2, or 3, and a column called y hat, which contains that predicted value. Given that data structure, we can now group by model, and then for each person, estimate the prediction error. The outcome was G3 log income, so the error is the difference between that true outcome and the predicted value, y hat. We then square that to get the squared error, and then summarize. Across all the observations in the test set, what is the mean of the squared errors? This table reports the results. So for candidate 1, we have a mean squared error of 0.439, candidate 2, 0.437, candidate 3, 0.477. Remember that we want a predictive model that predicts well, so it will have low mean squared error. So in this case, candidate 2 wins. It has the lowest mean squared error of the candidates we considered. Now I want to turn for a moment to think about train error versus test error. After all, we did this whole thing on the front end to figure out a split between a training and test set, and I want to think about exactly what that has bought us. So I'm leaving the code off this slide, but I re-estimated the very same thing we did on the previous slide, where I see our prediction error in the training set, the set of cases we used to estimate the model, and the test set, these cases that were not used to estimate the model. And what you see here is a few patterns. So first off, when we look at the train set mean squared error, it's lowest in the third model. Meanwhile, when we look at the test set mean squared error, it's lowest in the second candidate model. And so this relates to a pretty big idea. Within the train set, as you adopt a more complex model that has more terms and more interactions, you're giving that model more flexibility to approximate whatever patterns exist in the train set. And in fact, ordinary least squares exactly minimizes squared errors. So as you add more terms to the model, the trained set mean squared error for OLS will always go down. Meanwhile, the test set mean squared error may not always go down, because as you add more terms to the model, you're getting more flexibility, but you're also landing in a model that has more variance sample to sample. It's more sensitive to whatever idiosyncrasies exist in that trained set. So in this case, while a more complex model does better in the trained set, for our mimicked task, when we predict cases that we did not use for training, we actually are better off with a model that's not the most complex of the models we've considered. This is a very general principle that tends to be true, where as you adopt machine learning methods, you're going to possibly consider very complex models, and there's a limit to how much complexity your model can really handle in the training sample size that's available. Okay, so what happened here is overfitting. This is a case where candidate 3 is very flexible. It discovers patterns that do not generalize, and thus it performs poorly in the test set and the holdout set. So even though we might conceptually want to have these interactions, it's not possible to estimate them precisely enough in the data available to make them improve our predictive performance. Finally, we'll estimate in all of the learning set. So now we have our chosen model, parents' income plus race plus sex, as additive predictors for the respondent's log income as an adult. We fit that chosen model in the entire learning set in order to maximize our efficiency. And then we make predictions in the holdout set. And these are the predictions you could then upload to the submission site if this is your chosen model. So to summarize, the big idea here is that when selecting a predictive algorithm, you want to mimic the task you're attempting with the data that you have. So you never have access to this holdout set, but you know that your task is going to be to predict these cases drawn from the same population as your learning set. To mimic that task, you split your learning set into a trained set and a test set. This allows you to mimic the task you estimate in the trained set and then see how well you can predict in the test set. When you do this with many candidates, you can choose the candidate algorithm that does the best in the test set, and this gives you pretty good evidence that it might also do the best in the holdout set that you can't see. This is a general principle that I hope you take with you moving forward because it applies both to these statistical estimators we've discussed today and to the machine learning estimators that are to come soon.